All right, good morning, everyone. Welcome to week 8 of Mechatronics. I guess we are in the just in the middle of the semester. Um, Today, our laboratory uh, is related with a topic that is relevant for control systems and mechatronics. That is called system identification. This topic is huge in the sense of could is one of the main research areas in mechatronics and also for control theory and engineering. However, today we are going to have a hint of this system identification in order that you understand why this is important, especially when we are dealing with real systems. The main idea is that not always when you have a process or you have a real or physical asset, you not necessarily has a transfer function, or you cannot derive that transfer function from the fundamental laws like body, like free force diagram, uh, flow, mass conservation equation, and these kind of things. You cannot do that, or the system is too complex and you simply cannot do it. So you have to use numeric techniques, in this case, based on the input and output of the system in order to get that model. In this case, could be a transfer function or a state space, or even a nonlinear model that represents such system. So today tutorial, we are going to cover a Matlab system identification toolbox. That is like the main Matlab tool that we could use for this task of system ID. The main idea is that you can understand a little bit how it works and perform some experiments based on real data that we have from some process on the Matlab. So let's see. All right. This is the video tutorial session. Okay, let me minimize this. All right, just wait a minute, please. Hello, everyone. Welcome to week 7 lab. Can you hear the video? To system identification. This process is really important for our next step, that is controller design. Excellent. In the sense that Thank you. Develop the models or find the models for any system that we could have on real life. The learning objectives for today are developing fundamental skills for system identification using time domain techniques, understanding the difference between parametric and non-parametric identification techniques and when to apply each one, and performing some basic system identification from multiphysics models and real data coming from real systems. All right, so let's begin with a little bit of motivation. Why system ID is important for controls and mechatronics. Let's think in our baseline system, like this one, the spring damper one of our benchmark systems during all this lab. The mathematical model behind this spring damper system is pretty straightforward, as you can see here. You can see here the ODE representation. It's pretty much easy to obtain based on the second Newton law and free body diagram. And then we have the transfer function representation. This transfer function comes directly from the ODE representation, and we can have extra modeling like state space. This is really straightforward, and we can obtain really easy if we know the dynamic involved behind this model. Usually for this kind of model, we know the value of the mass, the damping coefficient, and the spring elastic models. So this is a really good example of a theoretical system with good approaches. However, if we jump now to other systems like this huge industrial system that we see here, so the situation is more difficult in the sense that, first of all, we have multiple subsystems that are interacting each other to perform this process. For example, we have a heat exchanger, we have a boiler here, we have some storage tank, and all the other subsystems that you see here, and each subsystem itself has its own constitutive equations and ODEs that model its behavior. Therefore, if we want to perform a control over this huge system, we can do it using the ODEs of each individual module. However, in terms of controller design, this could be really impractical in the sense that not necessarily we know all the details and parameters for each subsystem that we have here in this setup. And also there are some other parameters that probably we don't know because are manufacturer given ones and are not easy to identify or detect or calculate. So this could be somehow a problem. So the ODE modeling in this case for a, let's say, temperature control could not be the best way or the best approach. If we want to follow the MAD methodology, the best way to proceed is find an equivalent model of the overall process. In this case, based on the input and output that we want to control in terms of a state space or transfer function, which are the linear models that we see during the class. And based on these models, design a control system that satisfies that task, not necessarily knowing all the details of each system. So in this kind of complex assets is where system identification becomes relevant, in the sense that not necessarily we have to know all the details of each element in order to have an approximate model that allow us to design a controller and replicate the most important characteristics, behaviors from the overall system itself. So let's give a formal definition of what is system identification. Based on these Matlab definitions, we can say that system ID is a methodology for building mathematical models of dynamical systems using measurement of the input and output signals of the system itself. What it means? Usually we don't know the ODEs that satisfy the behavior of the system. The only thing that we have is the input and output data streams. And this is the most common scenario in industry and real life. We just have the input and output data. And based on this input and output data, we should be able to infer a transfer function model or a state space that explain somehow, in some degree, the behavior of the system that we have right now. Some of the features about this system identification is that it's applicable to any system. In real life, we are going to have to control some physical asset, and we only have those input-output streams. We can have parametric or non-parametric identifications models. We're going to see how we deal with that in the next slides. We just have the time series again. This and in that sense, based on this time series, we can infer continuous, discrete, or nonlinear models of that behavior. For our case in ME142, we are going to focus more only on LTI and linear models in continuous or discrete time. This is our approach for this course. However, as the complexity of the application increases, of course, we are going to need more robust models like nonlinear ones. Sometimes we may know some part of the physics of our system, not necessarily all of them, but maybe just a small part. And that can help us to increase our knowledge, but let's assume that in the more general case, we don't know a lot about the details and properties, exactly details and properties of our system. Something important, we can use this one for SISO or MIMO systems. SISO means single input, single output, or MIMO, multiple input, multiple output systems. For most of ME142, we are going to focus only on SISO systems. MIMO systems requires an extra degree of deep in control theory, so we are going to focus only on SISO systems for ME142. Maybe you heard about these white box, gray box, and black box definitions before, but if not, this is something that is totally related with system identification, in the sense that we can understand how our model is built. We have these three approaches: white, gray, and black box. The case of the white box, for example, is the case of the spring damper system that we see in a previous slide. We know all the physics, constitutive laws, and the parameters of the system. We know everything, and let's say that this is a white model. We know everything about it, and this is good. And also we can have some data streams available about that system, and that's much perfect. So the main point with this white box, we know all the math behind the model. That's something good. We have the opposite, that is the black box model. This black box model, we only have the input and output data streams. We know really few things or nothing about what is inside the system. And this is the most common real life scenario. Usually we only have the input and output of the system, and we don't know what is inside this black box here. That's the reason why it's called black box. The gray box, on the other way, is a mixture between white and black. We can know some things, like maybe some PDE or some transfer function inside this huge model composed by many subsystems, like the thermal system that we see before, and we have the input and output streams. However, we don't have the overall complete information. So that's the reason why we talk about gray box. Usually in industry, you will face more black box systems. You don't know what is inside, and if, according to the complexity of the system, could be really challenging to know with what is inside each block that you have. So based on this idea of white, gray, and black box, let's talk about really quick about types of system identification. Here we have basically two types of models, the linear models and the non-linear ones. In the linear model, the most common representations are the transfer function and the state space. In this course, ME142, we're going to focus more on transfer function. That is the one that we has been working from before. On the other way, we have nonlinear models. Those nonlinear models are quite more complex and involves a lot of nonlinear terms inside the equation that represent the system behavior. That's the reason why it's called nonlinear. This is just an example of a robotic manipulator, the most famous mechatronic system. This is the dynamical equation of the nonlinear model, where we have the inertia matrix, friction matrix, gravity vector, all of them in terms of position and velocity of the joints of the robotic manipulator in order to obtain the applied torque. The equation, for example, for a 3 degree of freedom manipulator could be something like this. As you can see, the equation for the three torques involves sine and cosine terms, as well as some parameters like theta 1, theta 2, which are in terms of some known things like the mass or the length of the manipulator links. Probably we don't know the inertia of the link. And This one here comes from something called Lagrange Multiplier, in this case for this particular example of nonlinear model, which are not easily, we cannot find easily this type of parameters, even if we have a lot of information of the system. So this could be something challenging to get. So these kind of models, of course, are more complicated. We are not focused on these nonlinear models for this ME142 course. We are going to be here with transfer function and probably state space. Based on these linear models and state space representations, we can talk about non-parametric and parametric identification. The non-parametric identification means that we can obtain a general model for the system. It means a transfer function or a state space based on either step, impulse, or frequency responses. That can be done using some methodologies like correlation, periodogram, impulse response again, that can be applicable. In the case of parametric identification, we already have, for example, a transfer function, and we want to find the parameters of that transfer function. It means that we are limited in the sense that we know how many parameters we have. In the sense of non-parametric, we can, according to the order of our model, we can create a huge order model as we need. In the parametric, we already know how many parameters we have. For example, this nonlinear model, we already know that we have this theta 1 to theta 14 parameters. So this could fit inside this type of identification. This identification has another techniques to perform, like least squares, maximum likelihood, or prediction error minimization. Covering all these techniques is itself just part of a huge course called system identification. We don't have time to go through all the single techniques. However, we want to show you a little introduction about this landscape of system ID. Okay, so based on that, that we can have linear, non-linear, parametric, non-parametric, let's define the steps that we require to perform system identification. First of all, we have to select an input signal that that make the system show its real dynamical behavior. Usually we can do this using step signals, sine wave signals, impulse signals, or any other type of signals. In our case, we're going to focus more on step and impulse responses. The second part, we are going to acquire the output of the system for that specific input. That's the requirement in this case. Once we perform step 1 and step 2, the third step is choose a model, either a transfer function, either a state space, either a nonlinear model that represent my behavior of my system. Then apply one of those estimation methods mentioned before in order to find the model, the chosen model, and at the end evaluate the model fitness and see if our estimation fit with the data that we have identified before. So that's like the main flow for system identification. Take the signal, choose the input, capture the output of the system based on that input, choose one model, apply the technique and find the model based on the data, and then evaluate if that model fits the original data. If not, basically we have to repeat these 5 steps again and again until we find a model that properly represents our system. That's the main idea in this case. All right, so we can simplify in our case the identification tool job using the Matlab system identification toolbox. This toolbox is basically a graphical user interface like this where we can put the input and output data and perform data model estimation using all the methods mentioned before. This toolbox already include and incorporate all these single methodologies, and based on these methodologies, we can choose and determine our model, the most suitable model for the input-output data that we have. In addition, we have pre and post-processing tools that help us to clean the data and evaluate and assess if our model has a good or bad fitness. That's the main idea in this case. So for today's tutorial, we're going to cover two systems. In this case, one is the RC circuit based on Synscape, and the other one is the spring damper. I guess you remember this one from this previous lab, and also this one too. So today we're going to go more into system ID in order to perform the methodology mentioned before. All right, so let's go to Matlab. As you will see, your lab assignment, you have to type these two commands in order to open first the RC circuit and then open the spring damper with input in this case. Notice that we are going to use Synscape models in order to apply some signal and then identify the transfer function, trying to be more close to real life examples. Of course, here we know many things, but the main idea is apply this methodology, and that can be extended into any other general case. So let's start with RC circuit. As we remember from previous labs, RC circuit corresponds to a first order system, which is one of the most common systems on control theory. If you see this particular implementation from this example, we have here the transfer function of this RC circuit, and we have also the R and C, the Synscape, response. So we are going to do the following. First, we're coming here. We're coming here to save. I'm going to my lab folder, in this case, this one. I'm going to save a copy of this model. Let's set RCID. Okay, it's saving my model. As you can see here in the folder, is the same that I just saved this model. Now, if we simulate this model as it comes, we will see, okay, I just have to run again. You can see here the response of the system, that is basically this one here. We see the charge and discharge behavior of our system, which is something that we expect and we like to obtain. Okay, let's do something. Let's go into call and step signal. Let's say that we have a step in time 0. The initial value is 0. The final value will be 5 volts. Let's going to replace here. Just going to connect the step input that we place here. This is just the transfer function representation, just to compare the Synscape versus the transfer function. That's the only difference itself. Right now, I'm going to include the block from, to workspace. I'm going to copy the mux, the multiplexer. We already do that before. Let's go into set here. I'm going to do this and this. Basically, what I'm doing is I'm sending to the workspace the output and input signals that we are going to use for system ID. We need the stimulus signal and we need the output signal. Maybe for your information, we can do something like this. You can double click over a wire and just put a name YT, and you can do the same over this one, UT. This is just to label the cables. Labeling the cables will help you to know which signal exactly is going through each cable. Just matter of notation. We need to go to model settings now. Here we don't need huge simulation time because this is just a RC circuit. We can come here. We are going to change the simulation time to fixed step. We're going to choose 5 power of minus 4, 5 power of minus 4. This will be our sampling time. It's small, but considering the simulation time, this should be enough. Let's going to configure the sim out block. I'm going to set here RC ID. Let's set RC, the RC data. We can save this in different formats like time series array structure. Let's save just as time series. We are assuming that the same sampling time is the same of the simulation. We're going to apply. We're going to say OK. Let's go and simulate the circuit response. As you can see here, after some time, our circuit reached the desired response. Something that we have to notice, and it's important to know, is that right now, because this is a simulation, we know the value of the capacitor and we know the value of the resistor. We know that. But because it's a simulation, in a real life, we don't know which value each represent our system. This is something really important. In the simulation, we know what is each one, but in real life, we don't know. Keep that in mind always. All right, so once we do that, let's go here and let's going to open the system identification toolbox. Wait, let me clean my command window. When you want to open your system identification toolbox, you type the word ident on the command window. This is the interface. Let me explain you a little bit how it works. First of all, you have to import data. In this case, the input and output that we generate from the simulation. Here we choose some pre-processing operations like merge time series, select on branch, remove means, trends, filter data, resample data, transform data, whatever that we want to use. And here we have the different methods to estimate mathematical models, in this case polynomial models, process models, spectral models, correlation, transfer function models, state space. It is really huge and complete, everything that we have with this toolbox. So based on this interface, we will import our data here and then we estimate the data, and here we can see here we will see the obtained models. So let's do with an example. Where I'm going to import data. We can import data in time domain, frequency domain, or a data object. Right now we are going to work only with time domain because this is the signals that we have, time domain signals. Let's click here in time domain data. Okay, it's open here. I just want to show you something. Okay, this is time domain signals from the simulation. Our time domain signals are saved here in RC data vector, time series array, sorry. If we came here we can notice that the first vector of the time series is the output and the second vector of the time series is the input. Therefore, how we can access this data? We just set the following. First of all, we have to verify that the RC data array is here in the workspace. Second of all, let's type the name RC data. By definition, if we double click here, this is our data series object. We have some time vector, data 1, that is the output, data 2, that is the input. Let's set something like this, rc data.data. In this case, check this notation. Let's check this notation here. As you can see, you see this is 2 points, comma 1. We are going to access all the rows of the column 1 that represents, in this case, okay, this should be 2 because input row column 2 is the input. And let's copy the same here and let's set that this is our input. We can put a name to this dataset. Let's call RC. This is really important. These two properties. Starting time is the time of this when the simulation starts. In this case, the simulation starts at 0, so always put 0 here. Now here, which is your sampling time, is the simulation sampling time. When you have real data, this sampling time is the sampling time of your data. So for our case is 5e minus 4 for this case in particular. So once we have that, we click on import. We came again to the interface. Okay, in this case, I repeat, this process was repeated twice, no problem. If you want to see the data that you just acquire, you can tick here in time plot. You see that the input is 5 and the output is this one, and we have the time axis, the same as we have on the simulation. It means that the data that we read is correct, input and output. U is input, Y is output. Keep that in mind always. You can check also the spectrum data. If you want to do frequency analysis, this is the periodogram. We don't want to go through this part today, but we have the option to see this one. Also, we can see some another frequency analysis. So this is another of the features. Right now, just focus on the first one, time plot here. Now, some important things. We could have many datasets here that we can import. However, we have to choose with which data we want to work. In this case, we want to work with this one here because we just have one. By default, Matlab choose the one that we have here as working data. And also we need a validation data. Because we have only one dataset, by default, Matlab choose the same working and validation data as the same. But just in this case. All right, so we can do some pre-processing like filtering, resample. Right now we don't need that one because we acquired this data from the model, so that's okay. Okay, now once we have our working data, validation data, we don't need to do any pre-processing. Let's do an estimation. We want to estimate a model of the system. In this case, we want to estimate a transfer function, but a transfer function familiar to us, in this case, first order, second order, or third order system. In that sense, we can use process model here. We just select process model on this estimation pop-up menu. we will have this interface. And here we can choose the transfer function that we want to identify. For example, here we can choose the number of poles. If we want to introduce delay, if we want to introduce an integrator, if we want to introduce a zero on the transfer function. If we keep just in this way, we can see that this is the typical first order system transfer function, k over 1 over tau s plus 1. Let's try with this one. That is basically this is the standard transfer function for a first order RC circuit. We can choose here many other different options, but most of these options are really advanced, and right now we don't need these ones. We'll need many of these options right now. We are just going to estimate, so just click here on estimate. Matlab is going to run the identification algorithm. It will take some time. Once it finishes, you will see here in model views, you will see that this new P1 appears. So if you want to see the response of this model, you tick here in model output. All right, in this case, we have a perfect matching because we came from the scenescape. We have a perfect matching, 100%. If you want to just display the original data, you just click here and you will see only the original data. Then you came here and here you have 100%. Okay, this is one model. However, the main idea of system identification is identify different models and see which is the best one that we could use. Right now I'm going to identify a second order model. You see now that here we have two poles. Let's go to estimate again. Okay. Let's see the difference. Okay, in both cases, the response is pretty much the same. 100% for this system identification. This is a really simple system. This is a really simple system. The RC circuit. We can choose, for example, 0 poles with integrator. Let's try this one. I just want that to show you something. In this case, as we know from our previous knowledge, the system is a first order. It's not an integrator. Therefore, the fitness of this system will be really, you see, this red line, this corresponds to this integrator transfer function, which is basically an unstable system. This is no good, and definitely this fitness is not going anywhere. So in this case, maybe the first and second order model will be enough for us. If you want to shut down the last model, you can just tick here over the model and you will have only the other two. All right, so now if you want to check the transfer function coefficients, you do right click over, for example, P1, and you have all the details of your system here. For example, this is our first order system. We have here 1, 2, 3, 4. This is 1 times -4, roughly. Tau, our gain is 1. If we came here to our constant C in this case is about 1 times -4, therefore we are fine. It means that our system time constant is correct in this case, based on what we find here. Remember that this tau is RC, so this transfer function, in this case, matches with the physical parameters, which is something good. We have any other tools that we can explore, like for example, we can explore here the root locus map of the transfer function. In this case, you can see here one of the poles is in -1000, so the system is stable. The other one -1000 and 2000, so super stable. And the last one is in the boundary of imaginary axis, so it's totally unstable. You can export these models into your workspace. You can just drag the model and here to workspace. And here you will have the P1 model. You can click and you will find the parameters of your model, as you can see here. It's pretty convenient, pretty straightforward. So our model parameter, our system identification toolbox is really good to do this kind of system ID. Now I'm going to do something in addition. This is a really idealistic case where basically our inputs and outputs are perfect. But what happens if my output has noise? Let's add some noise to my output here. Let's set random number. Okay, this random number has mean 0, variance 1. Let's going to set just variance 0.1. Let's simulate again. I'm going to simulate again the block diagram. Okay, I have to fix something inside here, and it's the sampling time. The sampling time by default is -0.1. 0.1. I'm going to type -1 in order to use the same sample time from the whole model. All right, let's check the response. Okay, I know what is the problem now. Basically, I'm just drawing the response without noise. Now I'm going to draw with noise. Just change the cable. You see that now we have a lot of peaks here, undesired peaks. So we don't want essentially this type of peaks. However, in a real system, this is a really common scenario that our measurements has some noise associated to it. So think that in industry you will find this kind of data. So I run my model, I log into my RC data. I'm going to log, now I'm going to log I'm going to log a new data set. Again, came here to time domain data. Basically, I'm using the same structure, so I'm going to import again using exactly the same parameters. Okay, I made a mistake. My starting time is still 0, so I'm going to put here. Let's plot the responses. You see the difference? When I put 1, it starts really far and it's not related with the real behavior. I'm going to switch the other one. I'm going to stop. I'm going to switch that one. I'm going to redraw the response. This is more the response that we want. I'm just showing the one that I want. Basically, this response here it doesn't work. So I'm going to the trash and put in the bin. And basically, I eliminate that data set. Every time that you want to eliminate a model, you just drag to here and should be eliminated from the interface. So now I have 2 data sets. I'm going to change my working data. I want to identify now a model, but using the data with noise. And I'm going to change my validation data to the noise data one. Again, let's go to process model. Let's go to first order. Classic first order model, as we can see. Oh, it goes really fast. Let's check it out. I'm just, okay. Now you see that my fitness goes down. This is because this random noise. Let's choose, I'm going to turn on the first model that we find. You see that in this case, this one regarding to this data has a really slightly difference on the fitness. No worries so much about that. But in this case, the main point here is that the presence of random noise is going to difficult for us the system identification, especially if our system has more severe noise. However, if we basically perform like an average of this noise, we can see that this behavior could be the one more representative of the system. Let's check the parameters of the new system identifier. You see that here the gain Kp and the time constant are slightly different, but this is because of noise. However, we are still getting a good response even with this noise. In real life, again, this is a common scenario, but this representation is really good. So we can have this one. Let's identify a second order model with noise. Okay, you see that the difference is slightly better, 69.29, and the other one is 68.85. In this kind of cases, these slightly differences are not totally representative on the system behavior. So for this kind of first order system, it's okay to set that using just one, using this first order model is enough to represent the system behavior. Take this into consideration when you are answering the questions of your lab. Okay, you can save the session. Let's click here, save session as. Let's save RCID record. Let's call it that way, record. You can save this session with all the data and the models identified. You can close the event. Okay, let's set yes here. It just saves some system ID GUI variables. Anything doesn't matter with our identification itself. I'm going to open the ident tool again. I type ident. You came here, you can open your previous session. In this case, you have everything that you do before here. And it means that you can still work in and perform any other identifications. All right, so let's go for the second model. In this case, I want to give you some hints in order to perform the system ID for the mass spring damper system. The procedure is exactly or pretty much the same that we follow with the RC circuit. The difference is that by nature, the spring damper system is a second order system. We're going to use this example. Again, let's save a copy. Okay, let's go here to my Lab07 demo. Let's set spring damper ID. Again, we can just, right now we are going to open loop identification. I'm going to erase these blocks. Right now we don't need it at all. This will be my system input, the force applied to the system, and this will be the output, that is the position of the spring damper. So here we are going to put from a to workspace again. similar to the previous one. Let's set here spring damper, SD data. Let's going to take a step. I'm going to apply a step in this case. The step is going to be at time 0. The final value will be 1. We can change these values, the default values here. I'm going to set, I don't know, 1. I'm going to set, I don't know, here 10. You have your own values on the lab assignment. I'm just doing this here as example for you. Let's set the multiplexer in this case. I'm going to take, okay, I'm taking the input, the output, that is the motion sensor. I'm going to take in the input here. I'm going to use the same structure that we used before. Just trying to be consequent. Let's set here the model system again. Let's change to fixed step. In real life, you always have fixed step systems in the sense that you have some sampling time. So think about that. I'm going to set up the time to 0.05. That's enough sampling time. Let's run the simulation. Okay, I missed something. I'm going to set up a scope. I'm going to set up the scope here. One is the input. The other one will be the output of the system. Let's play this. You see in this case that the system has a huge oscillation. Maybe we need to simulate for more time. Let's set 100 seconds. I guess should be fine. Okay, you see that because I changed the damping and stiffness coefficients, we have a huge transient response. That's okay. Don't worry about that. That's the system response for this step input signal. This is the position of the spring damper system. We have spring damper system data. I'm going to show you here to ident. Let's import data again. In this case, the structure is sd data dot data 2, and if you check the structure, will be exactly the same from the previous one. Let's call this one spring damper. Starting time 0, sampling time is 0.05. Remember, always do this thing. Okay, it's importing. Let's check the response. Exactly the same that we get from the system. We can estimate again a process model. Let me estimate a first order for now. You can see here. You see here that in this case, the first order is not the best model that you can use. It's too simple for this system and it's meaningless. So let's repeat again the experiment, but now with a second order system. Let's see how it works. Okay, that's definitely no good. Because we have real poles, let's try with underdamped poles. I mean, right now we are considering damping coefficient and natural frequency of the system. You see that now our fitness increase. This is because this model is better represented by the second order system. I mean, we know that from the nature of the spring damper system, but this knowledge about the system can help us to identify and understand if our parameters are correctly identified. In this case, we have this one here, and we can check all the model parameters. Now I'm just going to show you something really quick. If you came, okay, guess this is what you can do. If you have, for example, for your lab, you will have here, let me show you, you will have this dataset for your lab assignment. This dataset that I just imported has these variables sim_out and t_out. The first one is the input, the second one is the output. This data corresponds to a real data that I obtained from a thermal process in the lab, in Matlab. You have to identify the best suitable model for this dataset. Now that you have these sim_out vectors, you can do exactly the same that we do for time domain data. You can came here like sim_out and set, I don't know, the input is 1, sim_out, that's the name of the array. 2, you can call in a different way. Sys1, starting time is 0. The sampling time is 1. It's quite different. I can show you here the response. You see this response here? It's quite different. This is from this real data from a real system, a thermal system. You see the time scale is quite long to take this data. And you see the response in this case. This is like a sequence of steps. So now you have to find, according to the assignment, the most suitable transfer function that represents this system, as well as perform the other assignments. I think with this we finished the tutorial. Thank you so much for your attention. And if you have any questions, please go ahead during the lab session. All right, I think this covered the tutorial for today. If you have any question, please do it. Just raise your mic or use the chat box. By any means, we will take your questions. At this moment, do you have any questions? Okay. So please begin working on the lab. If you have any question, just raise your mic or use the chat box. Yes, Eddie, you have a question? You can disconnect now if you have class after this lab session. I'll be here up to noon. If you have more questions, you can do it during this time or join to office hours. Thank you so much for your attendance today. Listo.